October 14th, 1942. Henderson Field, Guadalcanal. The air is not air. It is a physical weight, a suffocating wet blanket of 105-degree humidity, coral dust, and the sour tang of aviation gasoline. Dawn is a reluctant grey smudge bleeding over the jungle canopy, and it brings no relief. It only brings the promise of noise and death. Lieutenant Frank Jensen, USMC, squints into the cockpit of his aircraft, pistol packin' mama. She is an F4F4 Wildcat, serial number 3417, and she is exhausted. Her blue-grey paint is flaked, revealing the silver skin beneath, which is itself pockmarked with patched 7 minuted bullet holes. His crew chief, a man named Sarge, who hasn't slept in 36 hours, leans against the fuselage. His knuckles raw and black with grease. He holds a lukewarm canteen cup of what might be coffee, but smells more like burnt mud. "She's topped off, Lieutenant," Sarge says, his voice a gravelly rasp. "Oil pressure looks acceptable, but she's running hot. She's always running hot." Jensen nods, saying nothing. He runs a gloved hand over the propeller blade. It's a Curtiss Electric, the best they have. 3 thick blades pitched by a small, whining electric motor in the hub. It feels solid, but he knows it's a lie. He knows it's secret. Jensen climbs into the cramped metal seat. The cockpit smells of sweat, oil, and fear. He straps himself in, the buckles hot and sticky. He begins his pre-flight checks. His motions automatic, but his mind is screaming. He is thinking of yesterday. He is thinking of Butch, his wingman, who isn't here this morning. He remembers the radio call, a high-pitched shriek of, "Zero on my 6, I can't shake him, I can't..." And then static. The Zero, the Mitsubishi A6M. It is not a plane, it is a ghost. It is a scalpel against their baseball bats. It turns on a dime and climbs like a rocket. Jensen and his fellow pilots have one rule, hammered into them by their CO, Joe Foss: don't you ever try to dogfight a Zero. They are to use their Wildcat strengths, its heavy 50 caliber guns, its armor, and its surprising roll rate. They must dive, fire a burst, and run. But to run, you need speed, and to get speed, you need the engine's power, and that's where the lie begins. That's the secret of the Curtiss propeller. A distant, rhythmic whoomp, whoomp, whoomp shakes the ground. It's washing machine Charlie, the nightly Japanese artillery shelling. But this is different. It's closer. A siren cuts through the humidity, a desperate rising wail. "Scramble, scramble, bandits inbound, 10 miles north." Men drop tools, canteens, helmets. They sprint. Jensen's heart hammers against his ribs. He finishes his checklist, his fingers flying over the switches. "Contact!" he yells. Sarge grunts, and the inertia starter whines. The Pratt & Whitney R1830 twin Wasp engine catches with a belch of oily blue smoke and a deafening roar. The entire airframe shudders, vibrating so hard his vision blurs. He gives Sarge a shaky thumbs up. Sarge slaps the wing and runs for a foxhole. Jensen taxis onto the perforated steel plating of the runway, the Wildcat bucking over the uneven ground. He is third in line. The first plane roars, kicks up a cloud of coral dust, and lifts into the sky. The second follows. It is his turn. He shoves the throttle forward. The engine screams. He feels the propeller control in his left hand, the little toggle switch for the electric motor. He needs low pitch for takeoff, the blades flat, grabbing huge gulps of air. The motor whines, slowly, sluggishly, adjusting the blades. "Come on! Come on!" The plane accelerates, but it feels sluggish, heavy, like it's dragging an anchor. He lifts off, wheels up and joins the formation, climbing into the hazy sky. And then he sees them. High above, silver specks glinting in the new sun. They are Zeros, at least a dozen of them escorting a flight of Betty bombers. The Zeros drop their tanks and dive. The fight is on. Jensen picks his target, a bomber, and lines up. He doesn't see the Zero dropping on him from the high 6 o'clock. His radio crackles. "Brake, Jensen, brake right!" He slams the stick right, his Wildcat groaning in protest. The red traces of the Zero's cannons flash past his canopy. He is in a defensive spiral. The Zero is on him, matching his every move. Jensen knows his only escape is to climb or dive. He shoves the throttle to the firewall, demanding every ounce of power from the R1830 engine. The engine wants to give it, but the propeller can't keep up. He tries to toggle the switch to a finer pitch for the climb, but the electric motor is too slow. The engine over-revs, screaming in a high-pitched wail, the RPM needle buried in the red. He is losing power, not gaining it. The propeller is cavitating, churning the air uselessly. The Zero, lightweight and efficient, simply pulls its nose up and climbs above him, effortlessly, like it's tied to a string. The Japanese pilot is now above him, inverted, looking down, preparing for his final fatal gun run. Jensen is trapped. He is out of altitude, out of speed, and out of ideas. What no one knew was that this moment, this precise geometry of failure, would change the war forever. The solution was not in the sky over Guadalcanal, but in a dusty blueprint, in a file marked "Rejected" on an engineer's desk thousands of miles away in Connecticut. The year 1941 is a catastrophe for Allied air power. The Zero shock paralyzes commanders from Pearl Harbor to the Philippines. The Japanese Mitsubishi A6M Ryzen, or Zero, is a weapon that defies Allied doctrine. American and British aircraft are built for ruggedness, armor, and firepower. They are heavy. The Grumman F4F Wildcat weighs over 900 pounds fully loaded. The Zero weighs just 300 pounds. This disparity in wing loading gives the Zero a supernatural ability to turn and, most devastatingly, to climb. Its Sakai engine is less powerful than the American twin Wasp, but it doesn't matter. The Zero's entire design is a symphony of lightweight efficiency, allowing it to climb at a staggering 5,000 feet per minute. American pilots, pulling back on the stick of their P-40s and Wildcats, find their planes wallowing, stalling, as the Zeros simply walk away from them in the vertical. The problem is a crisis of physics. The Allies have powerful engines, the Pratt & Whitney R1830 and the later R2800 Double Wasp are marvels of engineering, churning out over 1,800 horsepower. But that power is useless if it cannot be efficiently translated into thrust. The entire system hinges on the propeller. In the 1930s, aviation made the leap from fixed-pitch propellers, essentially a single-speed gear, to variable pitch. This was a revolution. It allowed a pilot to select a low gear, flat blade pitch for the high torque, high RPM needs of takeoff and climb, and a high gear, coarse blade pitch for the low RPM, high speed efficiency of cruising. But the system in 1942 is still crude. The dominant American design is the Curtiss Electric. It uses a small, fuselage-mounted electric motor, a governor, and a reduction gearbox in the propeller hub to turn the blades. On paper, it is precise. In reality, It is a nightmare. The system is heavy, complex, and, worst of all, slow. It takes several seconds for the motor to cycle the blades from fine to coarse pitch. In a dogfight, seconds are an eternity. A pilot like Frank Jensen diving on a target would push his throttle, but the propeller would lag, forcing the engine to over-rev. When he pulled up to climb, the prop would be in the wrong gear, and the plane would mush, its engine screaming uselessly. Furthermore, the system is electrically fragile. A single 7mm bullet severing the wrong wire renders the entire system dead, the blades frozen in their last position. Pilots report props running away, suddenly shifting to high pitch on takeoff, causing the plane to stall and crash. The U.S. Navy and the Army Air Forces are desperate. They throw money at new airframes. Grumman is already designing the F-6F Hellcat. Vought is building the F-4U Corsair. But these new planes, these monsters of horsepower, are all being designed around the flawed Curtiss electric propeller. The bureaucracy is locked in. The problem, they insist, is maneuverability and armor. The propeller is a solved issue. They convene boards, they write reports, they demand lighter planes, bigger guns, more armor. The suffering is immense. In the skies over Darwin, the flying tigers in China, and the jungles of New Guinea, the story is the same. A handful of Zeros decimates entire squadrons of P-40s. The kill ratios are terrifying, sometimes 10-1 in Japan's favor. Pilots are terrified. They are flying coffins. They know their engines are strong, but they feel like they are driving a muscle car that is permanently stuck in second gear. They are fighting their own machines as much as the enemy. The consensus from the top brass at the Bureau of Aeronautics, BUAIR, is clear. The Curtiss system is the standard. It is good enough. Changing the standard mid-war is too complex, too costly. The problem of the Zero's climb rate, they conclude, is an airframe problem that must be solved with the next generation of fighters. Experts agreed. It could not be done. East Hartford, Connecticut. The snow is piled high against the brick walls of the Hamilton Standard Factory, a world away from the coral dust of the Pacific. Inside, the air hums with the sound of lathes and milling machines and smells of cutting oil and hot metal. This is the domain of Erle Martin. Martin is not a hero. He is not a pilot. He is a quiet, bespectacled engineer, a slide rule man. He is methodical, precise, and utterly obsessed with a single, unglamorous concept: hydraulic pressure. Since the mid-1930s, Martin has been working on a revolutionary idea, a propeller design so complex and so advanced that the military bureaucracy has repeatedly deemed it impractical and unnecessary. He calls it the Hydromatic. His insight is simple. An electric motor is the wrong tool for the job. It is slow, weak, and vulnerable. The engine itself provides the perfect source of power, its own oil pressure. Martin's design uses a complex system of valves, pistons, and a centrifugal governor to channel the engine's oil under immense pressure to move the propeller blades. The system is not just a two-position gear shift. It is a true automatic transmission. The pilot simply moves a lever in the cockpit to select the desired engine speed, RPM. For example, 700 RPM for takeoff and combat, 300 RPM for cruise. The Hydromatic governor then does all the work. It constantly, instantly, automatically adjusts the blade pitch to ensure the engine never leaves that precise RPM, no matter what the pilot is doing. If the pilot dives, The governor automatically increases the blade pitch, making it coarser, to act as an air brake and prevent the engine from over-revving. If the pilot pulls into a steep climb, the governor instantly flattens the pitch, allowing the engine to remain in its maximum power band, turning every drop of fuel into raw, vertical thrust. It is, in effect, a constant speed propeller. It is brilliant, and the U.S. Navy and Army hate it. In 1938, Martin had presented his designs. A Navy commander reviewing the blueprints scoffs. "Mr. Martin, this is a plumber's nightmare. You have oil lines, pressurized seals, complex valves. What happens when a single piece of flak severs one of these lines?" "The prop is designed to fail safe, Commander," Martin explains, his voice steady. "It will default to a low-pitch setting, allowing the pilot to limp home." "It's too heavy," another official from Buer interjects. "The Curtiss is lighter, and it's electric. That's the future. Clean, simple." "The Curtiss is not simple," Martin counters, a rare flash of passion in his eyes. "It is a complex electrical system that is slow and underpowered. Your pilots in the field, they are fighting their props, the R2800 engine you're developing. That engine has 1,000 horsepower. The Curtiss propeller will waste half of it, the hydromatic. It will unleash it. The committee is unconvinced. The design is rejected for primary fighter contracts. It is deemed too heavy, too complex, and a maintenance risk. The Curtiss Electric is chosen as the standard prop for the new F4U Corsair and the early F6F Hellcat. Martin is devastated but not defeated. He and his team at Hamilton Standard continue to refine the hydromatic in secret, building it for civilian airliners and a few bombers. He knows he is right. He knows the pilots are dying because of this decision. He looks at the new specs for the Pratt & Whitney R2800 engine, a 28-litre, 18-cylinder behemoth. He knows that engine is a caged lion, and he is building the key. He will not wait for permission. Rentschler Field, Connecticut, spring 1943. The air is cold and smells of wet asphalt. A prototype of the new Vought F4U Corsair, the bent-wing bird, sits on the tarmac. It is an intimidating machine, the largest, most powerful fighter aircraft in the world, built around the massive R2800 engine. But it has a problem. The Navy test pilots hate it. Its stall characteristics are vicious, its visibility is terrible, and its Curtiss electric propeller creates so much torque and prop lag that it's almost uncontrollable on takeoff. The program is in danger of cancellation. Earl Martin sees his chance. He finds an ally, a grizzled Vought test pilot named Boone Guyton. Guyton is one of the few who has flown the Corsair and survived its quirks. He, more than any desk-bound admiral, understands the disconnect between the engine's power and the propeller's performance. "Boone," Martin says, approaching him in the hangar, blueprints in hand, "the Navy thinks your plane is the problem. It's not. It's the prop. Let me install my propeller off the books." Guyton looks at the complex, massive hub of the Hamilton Standard hydromatic prototype. It looks heavy. It looks complicated. But he remembers his last flight, fighting the stick as the Curtiss prop hunted for the right pitch. "Can you guarantee it won't tear the engine off the mounts?" Guyton asks. "I can guarantee it will give you control," Martin replies. For 2 weeks, Martin's team works in a guarded hangar, often at night. They are mechanics, engineers and plumbers, fitting the new hydraulic lines, installing the 400-pound propeller hub, and calibrating the delicate governor. It is a skunk works operation, completely unauthorized. The Navy brass, visiting the Vought plant, is deliberately steered away from this hangar. Finally, the day comes. Guyton straps into the Corsair, now designated Corsair X. The cockpit is identical, save for one new, simple lever for the prop governor. He starts the engine. The sound is the same. He taxis to the runway. He holds the brakes and pushes the throttle forward. The first test is a near disaster. As the engine hits full power, the governor hunts, the blades shifting pitch wildly. The vibration is so violent it shakes rivets loose from the cowling. Guyton yanks the throttle back, his teeth rattling. "It's shaking itself to pieces, Early!" he yells over the radio. Martin is white-faced. They've miscalculated the harmonic resonance of the R2800. They work for 72 hours straight, recalibrating the flyweights in the governor, a task requiring the precision of a watchmaker. The second test, Guyton, his faith shaken, eases the throttle forward. The engine roars, 200, 500, 700 RPM. The engine sound becomes a solid, unwavering, deafening thunder. The vibration is gone. Guyton releases the brakes. The Corsair does not accelerate. It explodes. It leaps down the runway, pinned Guyton back in his seat, and climbs into the sky at an angle that seems to defy gravity. He is at 10, Sunusarded feet in 90 seconds. He points the nose down, and as the plane accelerates, he feels the prop automatically bite harder, the RPM needle staying locked at 700. The plane is no longer a bucking bronco. It is a thoroughbred. He performs rolls, loops, and high-speed passes. He has total, perfect control. The rejected design has not just fixed the Corsair's flaws, it has created the most powerful fighting machine in the world. He lands, his knuckles white, but a massive grin on his face. He finds Martin. "That," Guyton says, jabbing a finger at the prop, "is the key. That's the only way this bird will fly. The data is undeniable. The secret is out. If you're hooked on this story, hit that subscribe button." Washington, D.C., June 1943. A humid summer haze settles over the Capitol. Inside the Bureau of Aeronautics building, the atmosphere is just as thick. A long mahogany table. Smoke hangs in the air from a dozen cigars and cigarettes. Admirals, engineers, and corporate vice presidents sit, stony-faced. At the far end of the table stands Erle Martin, a sheaf of papers in his hand. Next to him is a representative from Curtiss-Wright, looking supremely confident. The emergency meeting has been called to finalize the production order for the F-6F Hellcat and to decide once and for all whether to proceed with the F-4U Corsair for carrier use, given its abysmal test record. The Curtiss man speaks first. "Admirals, the Curtiss electric propeller has served the fleet faithfully. It is a proven, reliable design. The new models for the Hellcat are lighter and faster. The issues with the Corsair are, in our opinion, airframe related. This Hydromatic, proposed by Hamilton Standard, is a regression. It introduces complex, high-pressure hydraulics into a system that should be electric. It is heavier. It will leak, and it will be a maintenance nightmare for your crews in the field." He sits down to nods of agreement. The logic is sound. Adding more complex-sounding heavy equipment seems counterintuitive. Then Martin speaks. He is not a salesman. He is an engineer. He places his papers on the table. "Gentlemen," he begins, his voice quiet but clear, "the Curtiss representative is correct. The Hydromatic is heavier, by £212 to be exact. A low murmur of disapproval. Martin continues, "But those £212 buy you this." He unfolds a large chart. "This is the time to climb for the F4U Corsair with the Curtiss electric propeller. As you know, it is. Poor. This," he taps a second soaring line on the graph, "is the Corsair with the Hydromatic. It is 400 feet per minute. It is faster to 1500 feet than a Spitfire. It is faster than a Zero." The room falls silent. "You have built the most powerful engine in the world, the R2800. That engine," Martin presses, "is being choked by its propeller. You are not using its power. The Hydromatic is not just a propeller, it is the transmission that connects that engine to the air. It gives your pilots instant control, constant speed, and maximum efficiency. It will allow them to climb with the Zero and outdive him." An admiral at the end of the table, his face like carved granite, leans forward. "Mr. Martin, these are test field numbers. What about combat? The validation comes not in a boardroom, but in the sky. The decision is made, a massive, costly gamble. Production is changed. The new Grumman F6F Hellcats and the fixed F4U Corsairs are retrofitted on the assembly line, their problematic electric props torn out and replaced with Martin's plumber's nightmare. The first Hellcat squadrons, VF9, arrive in the Pacific in late 1943. The Japanese pilots, accustomed to their superior climb rates, are in for a shock. In their Zeros, they encounter the new, bulky American fighters and do what they have always done, pull up into a vertical climb to gain the advantage. But this time, the Hellcat stays with them. The American pilot, his R2800 engine roaring at a perfect constant 700 RPM, his Hydromatic prop clawing the air, simply keeps his nose up, lines up his 6 50 caliber guns, and tears the Zero apart. The result is a massacre. In the skies over the Marianas in June 1944, the new Hellcats and Corsairs achieve a kill ratio of over 19-1. The Great Marianas Turkey Shoot sees the end of Japanese naval air power. The rejected propeller, the heavy, complex, impractical idea, has single-handedly turned the tide of the air war. The legacy of Erle Martin's design is written in aluminum and steel, echoing in the roar of every high-performance piston engine of the war. The Hamilton Standard Hydromatic becomes the unseen, unsung hero of Allied air supremacy. It is not just the Hellcat and the Corsair, it becomes the standard propeller for the P-51 Mustang, allowing its Merlin engine to breathe in the thin air over 30 feet. It is fitted to the P-47 Thunderbolt, the B-17 Flying Fortress, the B-24 Liberator, and the British Lancaster. It becomes the tangible link between horsepower and victory. Over 500 Zulzer units are produced. Its reliability is so profound that it continues to be used for decades after the war, flying on the iconic DC-3 airliners that map out the modern world. Erle Martin is awarded the prestigious Collier Trophy in 1944. He does not become a household name like the aces who fly his invention, but his work is a testament to the power of the quiet, stubborn engineer. He returns to his drafting table, already working on the next problem. The human impact is measured in the pilots who come home. In the ready rooms of aircraft carriers, the terror of the Zero fades, replaced by a grim confidence. The pilots are no longer fighting their machines. They are no longer nursing a finicky electric motor, no longer dreading the prop runaway on a wave-off. A letter from a Marine Corsair pilot in Okinawa, dated 1945, reads, "We used to fear the vertical. It was their sky. Now it's ours. I can point the nose of this bird straight up, and the engine just sings. It doesn't scream, it doesn't beg, it just sings. I don't know who invented the prop on this thing, but I'd like to buy him a bottle." That pilot, and thousands like him, owed his life not just to the armor plate behind his back, but to the complex hydraulic brains spinning in front of his engine. He owed his life to an idea that was once rejected as too heavy. The story of the Hydromatic is a universal lesson. It is a reminder that the most spectacular wars are often won by the most unglamorous solutions. It is not always the sleekest airframe or the biggest gun. Sometimes it is the transmission. Sometimes it is the gear, the valve, or the bearing. It is the complex, impractical idea, perfected in secret by someone who refuses to accept that it cannot be done. The war in the Pacific was a war of energy, the energy to climb, the energy to dive. The Zero, for all its grace, was a lightweight with a limited engine. The American fighters were heavyweight brutes. Early Martin's rejected propeller was the key that finally unlocked that brute strength and focused it into a weapon that could not be beaten. What other forgotten stories of courage should we tell? Comment below.